4.2 is about the mean value theorem. Before we get to that, we have to talk about another theorem, and that is Rolle's theorem. And as just a reminder, this is something we've talked about before from grading FRQs. When you get to your FRQs and you're going to use either the mean value theorem or Rolle's theorem or some other theorem, if there are conditions that exist that need to be satisfied before you can use the theorem, you need to state that. There was a specific FRQ this summer that I graded where if you didn't state continuity, you didn't get the point, or you didn't state differentiability, you didn't get the point. So it's really important when we get to these that you state those. So we've got some function f, okay? So f would be continuous on this closed interval a to b. It would also be differentiable on the open interval a to b, right? Which means there's no, in this particular interval, there's no gaps, there's no jumps, there's no cusps, there's no sharp turns. It's smooth curve, or it could be a straight line. All right, and the endpoints have the same y value. Okay, so what this is saying is there's going to be some number in between a and b such that the derivative is going to equal 0, meaning somewhere along the way there's going to be a horizontal tangent, so long as it's differentiable on the whole thing. And so here's an example of what I'm talking about. Okay, here are the two endpoints a and b, where x equals a, so this would be f of a, x equals b, f of b. In order, since it's continuous, this has to connect somehow. In order to be differentiable, there can't be any gaps or sharp turns. So this would be one way to think about it. So there's going to be a number such that the derivative equals 0 at c. Now it could be multiple c's like this one. There's a horizontal tangent here, there's a horizontal tangent here. In order to get back to the other point, it has to have a smooth curve. Those are some examples. Here's an example, continuous horizontal tangent. Here's one that is not differentiable because I have a sharp turn here. So because it has a sharp turn, it's not differentiable. So this is not satisfied. This condition is not satisfied here. And so that's why there is no horizontal tangent. And then I gave one more example again where it might have an asymptote, okay? This is not continuous, so it doesn't satisfy this one, right? That's why there's no horizontal tangent here, no horizontal tangent here, because not all the conditions are met. When the conditions are all met, then this is what's going to happen. All right, so here's an example. All right, verify the function satisfies these three hypotheses of Rolle's theorem on the given interval. Find all numbers c that satisfy the conclusion. So I need to show that it's continuous from -6 to 0. I need to show that it's differentiable there. And then we have to show that the function at -6 equals the function at 0. So that's what this takes to do. You got to do all of those things. So continuous on -6 to 0. Okay, in order for this not to be continuous, this radicand, what's underneath the variable, or what's underneath the radical, excuse me, always must be greater than or equal to 0. Since my smallest number is -6, that's 0. Anything above -6 is going to force this to be a positive, and so it creates no problems. We're able to say that it's continuous. As far as differentiability goes, okay, what we would want to say is, you know, you want to think about what the curve looks like, and if you think about what the curve of a square root function looks like, it looks like half of a sideways parabola, okay? And so in this case, it's differentiable on those, and you could do the differentiation very quickly to determine that this is going to be fine. But most of the time with problems like this, you just have to state this. Now, you get in trouble if you just get in the habit of just writing it down every time and assuming it's differentiable, and then it turns out not to be, then you're going to have a problem. So just be very careful with that, okay? The next thing I have to do is prove that f of -6 and f of 0 equal each other. So when I plug -6 in here, this gives me 0, so this whole thing is 0. When I plug 0 in here, that's 0 times something, so they are equal, okay? And so now what I have to do is find the c values that will have horizontal tangents, okay? In other words, the derivative equals 0. So I am going to have to take the derivative of this. And this is going to require product rule. So when I do that, here's what I end up with. Looks like I'm missing one parenthesis here. Oops. There we go. Okay. The x times the derivative of this, that's 1/2 x plus 6 to the negative 1/2, plus the derivative of this is 1 times x plus 6 to the 1/2. And so now I need to figure out when all of this equals 0. Now the thing that is probably the easiest thing to do, and maybe you've seen, now we've seen enough problems like this, is when I have this negative 1/2 power and 1/2 power, I factor out the smaller one, which is, and now of course I'm going to plug c in, right? I'm going to plug c in and figure out, again I'm missing that parenthesis, because we need to find the c value, not the x value. And so from here, okay, that's where I was getting to that idea of factoring. And the smaller value, the smaller power is this negative 1/2. So that's going to come out in front. And so then I have 1/2 c. So this comes out, goes away. And when I factor this term out of this, it's 1/2 minus 1/2, which is 1. Still missing that parenthesis. I'll have to fix that. Okay. And you go, okay, well, what good is that doing me? I can simplify this. I can put this in the bottom. And so in reality, this is 1/2 c plus 1c, which is 3/2 c plus the 6. And then this goes on the bottom. And in order to find the c, in order for this to be 0, this top has to equal 0. So I just have to set these two things equal to each other. And so 3/2 c equals 0, subtract the 6. And now I just multiply both sides by 2/3. And then c equals negative 6 times 2/3. If this was an FRQ, you could leave it like that. But I want to know what the actual value is. And so c equals -4. So at c equals -4, that's where we're going to find a horizontal tangent on this interval. That's the Rolle's theorem. Now, the next one says, explain why this function does not satisfy Rolle's theorem. Okay, and so you have to answer the two questions, right? Like, is it continuous from 0 to 10? Well, think about what an absolute value function looks like. It's a v. It's continuous. It goes on in both directions, but it never has a hole in it or a gap in it or an asymptote in it. It is continuous v, right? What about differentiability? Is it differentiable, okay, on this particular interval? Well, because of the fact that it's a v, there's a sharp turn wherever that v happens. Well, you have to know where the v happens, and that happens when x equals 5. And if you think about this, that's where that sort of quote-unquote vertex, it's not a vertex because we don't have a vertex for a parabola, but you can think about it the same kind of way. And when x equals 5, I'm going to be at y equals 0. And so it is not differentiable. F of x is not differentiable when x equals 5 because of that sharp turn. So that's how you would prove that you cannot use Rolle's theorem. And the same thing is going to happen here with some things for the mean value theorem, which we'll talk about now. So here it is. This is in your book. Again, obviously you have this. But here's what this is saying and what makes the mean value theorem cool. All right. First, we still have the same conditions. F is continuous on the closed interval. It's differentiable on the open interval. Now, we're going to get even more specific with the mean value theorem. What it says is that the derivative is going to equal f of b minus f of a. Well, this is the slope formula, okay? And so what we want to think about, and then you could rearrange it too, but what this is saying is this is the instantaneous rate of change. We talked about rate of change earlier this year. The instantaneous rate of change is the derivative, is the slope of the tangent line. This is just the slope. And what this is the average rate of change. So what it's saying is there's going to be some value c. If these conditions are met, there's some value c where the slope of the tangent line equals the slope of the secant line. Okay? And so, in other words, the slope of the tangent line, if the slope of the tangent line is equal to the slope of the secant line, what does that tell us about the tangent line and the secant line? If you have two lines that have the same slope. Yeah, it means they're parallel. Let me give you a visual so you can see what that looks like. That's what this is saying here. Okay, so if mean value theorem states that given the right condition of continuity and differentiability on an FRQ, you'd have to actually write these things out. There would be at least one tangent line at x equals c, some c, on this interval, where that line is parallel to the secant line. All right, here's that visual. So here's a curve. Smooth curve, no sharp turns, no discontinuities. Okay, we've got an endpoint, so we've got continuity from A to B. We have differentiability. Okay, so if I found some value C, so here's my C value and here's my tangent line. What the mean value theorem states is that there's always gonna be at least one place where the secant line, that's when you just connect the points, is gonna be parallel to the tangent line. So here's that C value. Whatever that C value is, it makes those equal. The mean value theorem guarantees that that will happen if we're continuous on the closed interval and differentiable on the open interval. That's what makes it powerful. So here's the problems we're gonna look at. Verify that the function satisfies the hypotheses of the mean value theorem on the given interval. Then find all C numbers that satisfy the conclusion. All right, from 0 to 2. This is continuous. It's a cubic function. There are no asymptotes. There are no undefined values. So it's going to be continuous, and then it's going to be a smooth curve. So I know that it's differentiable. All right, so you got to say that it's continuous on the closed interval, differentiable on the open interval. And so then what we have to do is find the derivative, which is the instantaneous rate of change, and then the tangent, the slope of the tangent line, and then also the slope of the secant line, which is just the normal traditional slope, y2 minus y1 over x2 minus x1. But in this case, f of b minus f of a over b minus a. And so my derivative, when I take the derivative of this, I get 3c squared plus 1, and then that goes out. And then the average rate of change, f of 2 minus f of 0, when I plug 2 in here, I get 8 plus 10 plus 2, that's 10, minus 1 is 9 over 2. 10 over 2. My bad. 8 plus 2 is 10. 10. Oh, I'm forgetting to plug 0 in. My bad. Okay, so I get plug 2 in. Let's start again. 8 plus 2 is 10. Minus 1 is 9. Plug 0 in, I get negative 1. So 9 minus negative 1, this is 10 over 2, which is 5. That's better. Okay. What the mean value theorem guarantees is that there's going to be some C value that will let these two things be equal to each other. And so that's what we have to find. So 3c squared plus 1 equals 5. So that means 3c squared equals 4, which means c squared equals 4/3. So then I take the square root, and whenever I take the square root, it's plus or minus. So when I take the square root of 4, that's 2. The square root of 3 is 3. Now, the thing is we have plus or minus. The thing that we have to check is it on this interval? All right, well, I know if 2 over the square root of 3 was negative, then that whole number is negative, all right? So I know I can't have the negative. Then I have to see if 2 over the square root of 3 is in between 0 and 2. Okay, well, the square root of 3 is less than 2, right? Because the square root of 4 is 2. And so this is going to be less than 2. So 2 over 1 point something is going to be in this interval. So in the end, my only answer is 2 over the square root of 3. And if you needed to punch this in the calculator to verify it, you could. But the negative 1 is not in the interval, so that's why we throw that one out. All right? Now we do the same process here. for part B. So we have to, again, we have to state that it's continuous. Is this continuous? Now, we have an issue here, right? If x was -2, we'd have a problem. Well, -2 is not on the interval. That's the only number that would give us a problem. So we're good, right? It is continuous on 1,4. Differentiable, okay, again, the only spot it wouldn't be differentiable is where there was an asymptote or a hole or something like that, and that is not an issue, again, on the open interval for differentiability. So then we go through the same process. Find the derivative, then find the average rate of change, set them equal to, and solve. So the derivative, okay, low d high minus high d low, and I just went ahead and plugged the c in right away. So low derivative of this is 1 minus high, plugging the c in, derivative of this is 1 over that. And so this gives me 2, because the c's cancel over, c plus 2 quantity squared. Now hopefully this one I'll do better than the last one that I stumbled through, okay? This is f of 4 minus f of 1 over 4 minus 1. So f of 4, so I put a 4 in there, I put a 4 in there, that is 4/6. I put a 1 in there and I get 1/3, okay? And 4/6 is 2/3. So 2/3 minus 1/3 is 1/3, and so that's 1/3 over 3, so that ends up giving me 1/9. You can check me on that. 1/3 divided by 3 is the same as 1/3 times 1/3. So then I set these two things equal to each other again, and the way that I'm going to solve this is I'm going to cross multiply. All right. Quantity c plus 2 squared equals 18. Square root plus or minus. Now this one's a little trickier. I'm going to hang on to that minus for a second, because when I subtract the 2 over, I have to decide maybe both of these are going to be good, maybe not, all right? This number is bigger than 4 but less than 5. So if I had -2 minus -4-ish, I definitely get a negative number, okay? If I get -2 plus +4-ish, it's going to be 2 something, which is in the interval. So in this case, it's just the positive one, just like this one was. That is not a rule. It's always just going to be the positive. That is not a rule. You have to actually check it to see if it's in the interval. All right, next thing. Why does the mean value theorem not apply to the following solutions on the given intervals? So what we're looking for here is either a discontinuity on the interval or it's not differentiable on the interval. That's what we're looking for. If one of those things ends up being true, then we can't apply the mean value. So think about the tangent function. All right, the tangent is y over x. So anytime the x value equals 0, we're going to have a problem. So if you think about your unit circle, when is x 0? Well, x is 0 at pi over 2. X is 0 at 3 pi over 2. So we're talking here from 0 to pi. So we're just talking about the first and second quadrant. So pi over 2 is in the middle there, which means it's not going to be continuous there. Okay, not continuous at pi over 2, because at pi over 2, we're on the y-axis, the x value is 0. Okay, now, cube root function for these. Any issues here? I can have negatives in here. There's no issues for continuity. That's gonna, we should look at the derivative. Okay, and so, well, what is the derivative of this? Okay. I can tell you that it's not differentiable at 0. And you go, well, wait a minute. How can you do that without doing the derivative? Well, look at the derivative. This is the derivative. 1/3 x to the -2/3. Well, that means this goes down to the bottom. And so if x was 0, this whole bottom would be 0. And so that's where we have our issue. Those are our two two things to be looking for. Anytime you're trying to disprove or not use mean value theorem, or Rolle's theorem for that matter, you have to show that it's either not continuous or not differentiable on the interval somewhere, okay? And then the last one says, here's a graph. Use the graph of f to estimate the values of c that satisfy the conclusion of the mean value theorem for the interval 1 to 7. So we're only talking about from here to here, from 1 to 7. And so, in other words, what the mean value theorem, first off, it is continuous there, right? We can see that it's continuous on that interval. We can see that it's differentiable because there's no discontinuities, there's no sharp turns. And so what we're trying to find is where the slopes of the tangent lines are parallel to the slope of the secant line. So the first thing we want to do is draw the secant line. And those are those 2 points. So you have to find spots where there are tangent lines on this graph that are parallel to this. That's what you're trying to do. And so I can see 3 of them. One of them is very close to it right there. So here's this slope and this slope. Those look parallel to me. And so that looks like I'm calling it 4.5. You can estimate a little bit differently. Maybe I should have slid that over, but I think you get the point. Okay, then I'm going to have one over here, and I'm going to have one over here. So I got one there. I called that 2.7. And I got another one over here, and I'm calling that 5.8. So that's really the concept of the mean value theorem. There's going to be a spot, if it's continuous on the closed interval and differentiable on the open interval, where the secant line's slope is going to be the same as the tangent line slope. And so that's what all the algebra was that we were doing. We were finding the slope of the tangent line is the first derivative. The slope of the secant line is the traditional algebra 1 slope. And you just have to show that those are equal to each other.